Science and Technology Program, an integrative graduate educational and research traineeship, which is sponsored by the National Cancer Institute as well as the National Science Foundation. Dr. Sridhar has immense knowledge in the fields of nanomedical therapeutic applications and nanomedical development pathways. It's a true honor to welcome to the podium Dr. Sridhar. Thank you so much.
Well, it's a real pleasure to be here to come and tell you about our work on nanoplatforms for nanomedicine and telemedicine. And I actually must confess that I added the word telemedicine this morning. Primarily, however, I've always known that I worked in both these areas, but you know mentally, if you look at how these fields are perceived, they're perceived in two different worlds. And today, I feel like I've come out of the closet, and I want to actually, I want to take this opportunity to thank Martine and Baruch for really recognizing this convergence and holding this conference, and also for this liberating feeling I'm experiencing. But I think you'll see why actually, indeed, we are at a convergence, and how my own work, in fact, is positioned in this area. So first, let me add that I collaborate extensively, and particularly my collaborations run across several departments and several institutions. I am fortunate to be right next to some of the greatest medical research hospitals, and we collaborate with all of them. The essential concept of our nanomedicine research program is to address two key issues that I'm sure you all recognize. First is early diagnosis, and the second is targeted delivery. And the way we're doing this is through a variety of nanoplatforms, and I'll touch upon a couple of them today, which we are then essentially functionalizing to address the issues of diagnosis and therapy. In diagnosis, for instance, in imaging, we do a variety of modalities of intracellular and in vivo imaging. In delivery, we can deliver not just drugs, but also DNA and also localized energy. And we address several diseases, not just in addition to cancer, but also infectious and cardiovascular diseases. The key ingredients in this are two types of multifunctional nanoplatforms. One are these nanovectors, which can be functionalized in several ways. They may start with, for instance, a magnetic property, which we favor quite a bit, and I'm going to spend some time on magnetic nanoparticles. We often put a metallic gold shell on it. This is to assist in functionalization through using thiol chemistry, which is quite advantageous and robust. There's almost always in these a PEG spacer, which enhances circulation. And then on top of that, one adds several moieties, which might be either antibodies or fluorescent labels or drug molecules, and also genes for plasmid DNA for gene therapy. And we have a large, here I include my collaborators, several types of platforms that we utilize. Now, the other major platform that I'll talk about briefly is the nanotemplates. And the idea here is that how do we make surfaces that are actually already in place in the human body in implants better? Right now, they're not smart, and the intent is to make them smart through either drug delivery or through mechanisms to connect to. So here's one example of the use of nanoparticles for imaging. This is actually what we are doing here is we use silver nanoparticles, and we're looking at silver nanoparticles going through skin. There are several there's not only just the fundamental science issue of, what is the nature of the trafficking, but also to understand there'd be implications on toxicology, as you can appreciate. And so we have a rather unique instrument in which we can look at several modalities, including bright field, confocal reflectance, two-photon, and second harmonic. And these are rather special nanoparticles because they don't bleach and they don't blink, unlike other entities. And what I will briefly show you here is, excuse me, need to play the, yes, and here's the image. We actually take a Z stack of these images, and we're able to look at the profile of nanoparticles through them. So this project is looking at these nanoparticles, seeing how they diffuse through skin, and in the end, we hope to build up a body of knowledge on which would be useful for understanding some toxicological questions. I'm going to now turn to magnetic nanoparticles, and here there are several applications of magnetic nanoparticles in separation science, in MRI contrast enhancement, which I'll talk about, and in localized energy delivery, which I'll talk about, but also magnetic manipulation. That is, we'll use magnetic fields acting on these particles to actually do drug targeting locally. So this is the concept of the multimodal use of magnetic nanoparticles is to simultaneously be able to do, and not just to do, to visualize using MRI contrast enhancement, to target using magnetic fields, and also then locally deliver energy. And I'm going to show you some examples of all of this. And so this is actually a synergy of nanomedicine and telemedicine in the way that we're coupling. One of the first questions is, how do you couple energy locally to these nanoparticles? Here's a quick picture of these nanoparticles. These are well-known, and these are all FDA approved, so there's really no question right now of toxicology of the nanoparticles that we use. With Vladimir Torchelin, who's a leading pharmaceutical scientist, we have worked with him to incorporate these into immunomicelles, which he has actually pioneered. And then what we're doing is to create an entity which has long circulation, has 2C5 antibodies for targeting, and then we've done, and the magnetic property also, along with drugs. So this is an entity which incorporates true multifunctionality. And we've done a variety of animal experiments in these. And I can only show you, so the things we're trying to address here are targeting, visualization, and energy delivery. And here is a view of how these cells are incubated inside the cell. These nanoparticles are incubated inside the cell. These are red. The nanoparticles also have a fluorescent dye on them, and you can see that they're taken up by the cells. As you've heard several times, cells easily uptake a variety of nanoparticles, and these are also one of them. Now, another platform we've used are magnetic cationic liposomes. This is with Bob Campbell, another pharmaceutical scientist. And here, among the various major advantages that you can have much greater loading. And this, it turns out, is rather important for the kinds of things we're doing. So let me start with let me note that this is the fantasy that we started off with a few years ago, where you would come in and you would inject magnetic nanoparticles, and then while they would be circulating, you would turn on a magnetic field locally, which would then lead to them getting localized on the tumor. And then once you've done that, the next stage, of course, would be to turn on some agent which would then release the drug, and with the corresponding significant therapeutic benefits. And I'll show you the same how we're doing this in in animal experiments in our lab, we inject nanoparticles, and then we turn on a magnetic field. They localize, and I'll show you how we visualize all of this. And then the next step, of course, would be to release the drugs, and I'll show you where we stand on all of this. Now, with the immunomicelles, we've already shown that if you just take the bare nanoparticles, if you just take, say, the bare micelles or the drug, you have, with systemic injection, you only get to about 0.1% accumulation in the tumor. However, when you add the antibody, you can get up to 5% accumulation in the tumor. What we've also shown is that with a magnetic field that is using magnetic guidance, you can actually achieve another factor of 2 or 3. So we're already up to very significant dosages accumulating in the tumor, correspondingly with fewer side effects, which is the whole goal of all of this. So quite a bit of targeting is being achieved with with magnetic guidance. I want to show you, we're going to see how it actually localizes. And before that, I must also show you that the way you observe these nanoparticles is using MRI contrast enhancement. That is to say, the nanoparticles surround the relaxation properties of water molecules in their vicinity, and then you can observe it either in the form of T1 changes in the T1 relaxation or the T2 relaxation. And here's an example of how, with the really dramatic reduction in the relaxation times that you can see, you can get about 1,000-fold reduction in relaxation times compared to bare water. So you can see very significant contrast with these nanoparticles. And so using these magnetic cationic liposomes, this is a sort of angiogram which shows you how you can actually observe the nanoparticles. This is in a healthy, this is pre-injection and post-injection, and you'll see that these blood vessels actually went dark. This is where the nanoparticles localized. And here I'm showing you what happens in a sequence of scans, starting on the left with a healthy mouse. If you look at the kidney, this is pre-injection. After you inject, in 1 hour, you can see the accumulation in the blood vessels in the kidney. They're actually, again, these are much larger particles, so they're well above the renal threshold. And then after 24 hours, they're cleared. Well, they're not cleared in urine, but they're actually just getting out of the circulation. These nanoparticles do last for several hours during the day. Now, the next thing I want to show you is how putting a magnet on the mouse increases the accumulation in here. And here is on the left is a scan of a tumor-bearing mouse 24 hours after injection, on which the magnet was not placed. But here is one where the magnet was placed, and you can see here that this area around the tumor is much darker, which is quite a dramatic visualization of the fact that using magnetic guidance, you're actually sucking up these nanoparticles into these magnetic cationic liposomes. It's not just the nanoparticle, but the whole entity into the tumor. And there they would sit, and then they can release the drugs. So, so to summarize this part of it, they're very good contrast agents, and we're able to actually visualize and show that you have significant benefits from magnetic targeting. Now, once they're there, what would you do? And here is what we're working on with triggered release. The idea would be that you would then turn on these magnetic fields, and then they would disrupt the liposomes and release the drugs, so that you should see that the color of the, actually, and that isn't visible, but the color, the drug would be released and change the color of the solution here. And that actually that we have seen in studies where after we turn on the magnetic field, you can see the fluorescence of the doxorubicin increase. And so now we have, actually what we have done here is we have in fact come to the point where, if you remember that cartoon again, we're now able to, we've demonstrated that you can inject nanoparticles, you can guide them to the tumor, and then we should be able to, actually this part is still being worked on, but we should be able to then release the drug. Or we can also deliver energy using hyperthermia, which I'll turn to next. These nanoparticles are very efficacious for heating. And in fact, we can increase temperature very rapidly. And here I want to say that the technology is here. That's not the issue. But the real issue that I brought up earlier is that the clinicians have very clearly said that, you know, you have to take, you will not get into any, this will never get approved if you cannot prove that you can, that you cannot maintain the temperature locally. You can guarantee that it won't exceed around 43 degrees, because otherwise you'll kill surrounding tissue. Now, so this is now where nanomedicine and telemedicine converge. If you can deliver energy locally, you can do a variety of things, such as are listed here: hyperthermia, a drug release of various kinds, and I already gave you an example of that. We've killed bacteria very nicely, as I actually briefly showed you in the previous slide. But also you can do biomolecular modification, and we have an experiment on that, which I don't have time to discuss. The other platform that I want to say, and I'm going to say this rather quickly, is that now turning to the nanotemplates, there are a variety of implants that you all know about. Our goal is to make these implants better. And in order to do that, what we're using are ceramic coatings, which are nanoporous. Here are examples of these nanopores on alumina or titania. And the key point is these are non-erodible. So for instance, and one thing we've done is we've been able to assemble nanoparticles in these pores so that then you could have drug-loaded nanoparticles in there. But we also assemble carbon nanotubes, and you could do a variety of things with that too. Now, here's another view of that, showing the nanopores. But the point I want to make is that one of the big interests we have, and I'm getting quite a bit of interest from cardiologists, if you look at drug-coated stents, the major problem is the polymer on it can delaminate. These would be robust coatings. They would not delaminate. And so you would avoid a major problem. Now, with this in mind, how do these behave as drug-releasing agents? I'm going to quickly go through this. We load drugs, we measure it, we have set up our own measurement capability, and I want to show you that what happens in these is fairly characteristic. You have an initial burst release, and then you have a long sustained release over weeks. And so these are very good platforms for drug releasing. And the way it would work is that, you know, again, we've even worked out the model for it. It's actually a density-dependent desorption model. Now, we're not using this type of concept for a problem, which is that is implants that are already being used in image-guided radiation therapy. These are fiducial markers that we're coating. We can either prepare the surfaces directly, or we can put polymers on them. There, the delamination problem is not so severe, unlike in a cardiological situation. And so we have drug-loaded polymer fiducials, and I can show you how these drugs are released. And so the idea would be that you would have a region of radiosensitization, which would enhance the therapies. Now, besides the research, I'm also an educator, and we actually started the first nanomedicine program in the world. And this is thanks to the National Cancer Institute and the National Science Foundation. This is the sort of our worldview of education, which is interdisciplinary and incorporates co-mentoring, not just from academicians, but also from people like you, many of you, from industry, venture capitalists, and others. And I won't go into all. We've developed the first nanomedicine courses, and I'll just show you two of our illustrious graduates. And let me add that we teach not only to college, but all the way from K through 100. And so with that, I'm going to close here. I used to give this talk saying nanomedicine has an exciting future. I now say that the future is now, and I would urge you to join us. You can find out more on our websites here, and here's a cut from that. Thank you very much for your attention.
Great talk, Dr. Sridhar. Everybody who has questions, please take a stand at the microphone and introduce your name and whichever organization you'd like to affiliate with.
Okay, Ennio Tasciotti, Division of Nanomedicine, Houston. First of all, I'm impressed because I've used that movie with the magnetic field for years with my students, and I never know that it was you that actually
So it's not mine, by the mouse or the human?
The human.
That's Biofan.
Okay, I thought it was you. Okay.
Yeah.
Aside from that, the big problem that we have every time we talk to our clinician collaborators, they say that the real problem is not actually the primary tumor, because with surgical procedures, most of the times you can just get rid of it and you're fine, and you very often die of a metastatic disease. So how do you envision to apply that type of application to a metastatic disease where you don't really know where the problem is?
Right.
Thank you.
Yeah. So certainly that's a critical issue that has been also raised before. I think, well, for those, the specific chemical targeting is going to be critical. And, you know, we're not there yet, but the idea would certainly, you know, the fantasy is that the nanoparticles would really find out every cancer molecule, every cancer cell there is, and attach onto it, and then we would be able to deliver some kind of therapeutic benefit agent, whether it's drugs or genes or energy. So I think that is the long-term vision. We're far from that yet, but I think it's feasible. What we're now trying to really do is attack the low-hanging fruit, which are now not all tumors can be resected. My colleagues on the image-guided problem that we work with, they're talking about lung tumors, where we think there's going to be major impact of these things. Same with the brain, as you just noted. So yeah, and prostate, for instance. And
so one of the I'm sorry, Eric Jacobson, University of Illinois.
Thank you.
So one of the things that I have been educated about by a colleague here in Canada, Ann Chambers, is the role of clonal heterogeneity in metastasis, and the bottom line of that is that the cells that become metastatic foci may really be outliers in the large population of cells and not representative of the larger population of cells. So that, and one of the ways it occurs to me, I hadn't thought about this until the talks this morning, but one of the ways it occurs to me some of these might be outliers is that it may be that some of them are resistant to the heating and will still survive. So I wonder if there's anybody here who knows of any evidence one way or another as to whether cancer cells can develop resistance to thermal shock in a similar way to the way that they develop resistance to drugs. Or is this unexplored territory so far?
If no one else is going to take up, I wouldn't profess to be an expert in that either. Let me just say the whole issue of what heat does is actually quite, there are many mysteries to it. For instance, actually, we addressed we did our bacteria experiment to address the inverse problem to what you mentioned, because they have these persister cells, and they're not easily killed by antibiotics. And in fact, there's been no development of antibiotics for almost 30 years now, of new antibiotics. And so we thought this would be an alternative way to address that. As far as we can tell, we're getting 100% kills. But the problem, the challenge there, and this was with the dentist, was that we're elevating temperatures far beyond that would be allowed in a clinical setting. And so I think we've got a cure, but unfortunately it might be too good. So.
Gary Craig, University of Maine. As I understand it, with these magnetically guided particles, you hold a magnet near the tumor. I was just curious, for a tumor that's hard to get to, like the pancreas or the liver, what do you envision for that scenario?
Good question. But I think this question, the experiments are being done very crudely these days, just because in a mouse you don't need to do anything more. I see no reason why. We've got capabilities to design all kinds of magnetic field profiles, and I see no reason why you can't, devise an appropriate field profile which will concentrate nanoparticles that are quite far away from the surface.
Shui Li from Medical College of Georgia. One of the potential applications is that to develop some radio sensitizer reagent for the cancer treatment. And you just mentioned one sentence. What's your innovation about this strategy?
I'm sorry, can you ask? I didn't answer.
I just heard you just mentioned about radio sensitization, is that right?
Yes, I understand.
So
okay.
what's your, I'm in the field trying to develop some radio sensitizer to enhance the cancer treatment. So what is your strategy, in terms of?
Okay, the question, what we're trying to address is delivery of the radiosensitizer.
Okay.
So I assume you're in the business of making radiosensitizers, molecules, right? So you give us your molecule, we'll load it, and then it'll be the radiosensitizer.
Good.
So we're in the delivery business.
Good.
And actually, a lot of this is motivated. This brings up a thought here, which I'd like to convey. Having worked on delivering nanoparticles through, either chemical targeting or magnetic targeting, I'm trying now to exploit situations where there's already surgical intervention, there are implants that are already there, and then we're trying to make use of them, which I think are low-hanging fruit.
Thank you.
Hi, Linda McDonald Glenn from Albany Medical School. I'm an attorney and biomedical ethicist, and I saw in your slide, in your outline, that you had a little section for ethics there. I was wondering, and that's my field, so I was wondering if you could tell me how large a percentage of your time and effort is devoted to that. How big is your? Just talk a little bit about it.
Sure, but my own effort, I just think about it occasionally. And worry about it, like all of you. But this is part of this IGERT program. This is an NSF training program that we got funding for, and we're going for again. And here I would welcome collaborations with you, and including ethicists. The ethics is done by my colleague Ron Sandler. Really, he's the expert.
You, Blumberg, you spoke about killing bacteria during the talk, and then as answer to a question. Question is, has you made any attempt to focus on viruses to see the effect that might have? And the other, the notion of using this for diseases like subacute bacterial endocarditis, when you have the bugs trapped in a sense, and with this, very complicated thing that provides resistance, and also the formation of these biofilms, biomats, on implanted devices. And then I have one final question. What effect would these magnetic particles have on people, improving their ability to find magnetic north?
Well, on the second one, I don't know if we will ever be as good as the birds, which apparently find magnetic north and manage to build their lives around it. I'm not sure we have the neural capabilities. You'd have to build an implant, separate one just for that one. Okay. On the first part, I'm actually very enthusiastic about this type of treatment for bacteria. And I'm actually enthusiastic about all of this, okay? What I need are clinical partners who are going to be equally enthusiastic. And in this case, so we started off actually with the idea of addressing persister cells, biofilms, and so on. So what we have shown is we can deliver energy, we can heat things up locally. Now, the question is this gonna be okay in a clinical setting? So precisely for the kinds of problems you mentioned. So I'd be happy to work with anyone who, let me put it, the dentist with whom we worked with and did all these studies said, look, I mean, the temperature is too high. And also there were other issues. You're not going to use this, the dentists are not going to make money on this, which is a secondary issue. But that also plays an important role in what they will pursue. The limiting factor, we know this kills, we know it's quite efficient, but we've got to do it in a way where that we can do it safely. And that's really the limiting factor. But I appreciate all the questions that you raised, because that's why we started this.
There is an experiment, there are natural biomats which are common, particularly in extreme environments, which may be a potential experimental system.
That's true, right.
Thank you.